Hello friends, previous lecture we studied the composition of the two simple harmonic motions. Now today we see when a particle is performing simple harmonic motion, means a particle is in motion, means particle having a definite speed, then acceleration, then it performs some kind of displacement. When you say the particle is in a speed, particle is in a motion, means definitely the particle performing some kind of kinetic energy. This kinetic energy is a constant at every places, means the question is like this, the kinetic energy is same at mean position and at extreme position, or it is a different and it is a different at the mean and extreme positions. The energies are same or the energies are different. Okay, if the energies are different, then where the kinetic energy is maximum. Again question arises where the kinetic energy is minimum. If the kinetic energy is minimum at a particular place, then it will be very simple. The potential energy it will be greater at the particular place because energy is not created, energy is a constant. Means energy is converted from one place to or one form to another form. Means if the kinetic energy is less, means obviously potential energy is greater. In the same way, today we study the energy of a particle performing simple harmonic motion. So the title is Energy of a Particle. Here we study potential energy, kinetic energy and total energy of a particle performing SSM. Energy of a particle performing SSM. That is a performing simple harmonic motion. Let us study the different energies, that is the two different energies. Let a particle performing, and the particle performing simple harmonic motion means the particle performing to and fro motion or up and down motion. Here we say that the particle is performing to and fro motion, that is the particle follows the horizontal path. Let Mn be the two extreme positions where on which the particle performs the simple harmonic motion, it performs the to and fro motion. Let O be the mean position, equilibrium position, or at the central position of a particle performing SSM. Now initially the particle is at the point P. This point P is situated at a distance x from the mean position. Particle is situated at a distance x from the mean position or equilibrium position. Now we study what is the kinetic energy, potential energy, and then the total energy of a particle performing SSM. This O is my equilibrium position, or simply it is my mean position. Okay, this is my extreme position. This is also a negative or extreme position. Okay, these are my extreme positions. And this is the maximum displacement up to the n, that is called as the amplitude A. Okay. Now start. When a particle performing simple harmonic motion, then the restoring force acting on the particle is given by F equals to minus of kx. When a particle is at the point P, it performs very short displacement, let me call it infinitesimal displacement, and its value is dx. Okay, particle performing a very short or very in a small interval of time, that displacement is an infinitesimal displacement, very short displacement. Within a fraction of second, it performs a displacement. That displacement is an infinitesimal displacement. That displacement is a dx. Okay. What is the meaning of restoring force? Restoring force is always opposite to the displacement. The particle displacement towards n and the restoring force is at towards O, opposite to displacement. Here the infinitesimal displacement is towards n and the restoring force is bring that particle comes or try that particle to maintain its initial rest equilibrium or the mean position. Means that restoring force is always opposite. Okay. Therefore, here the small work done is there, and that work done is basic formula for work done is work done equals to force into displacement. But here the restoring force is always towards the mean position and displacement is away from mean position. Therefore, both are negative to each other. Now we substitute that work done dW equals to minus of value of F is minus of Ks into dx. That dW equals to small work done equals to Kx into dx. What is this K? This K is my force constant. That is a force per unit displacement. That is a force constant. What is the value of K? What is the value of K? That we have to also find out. But before that, when a particle performing very small displacement, then it goes from to this. Now the total work done is how much? How you find out the total work done? That we have to also see. To find out the total work done, integrate such a small displacements. So we integrate that dW. So we integrate that Kx into dx. Again see here, K is a constant. Therefore that constant is out of integration. So that term remains integration of x into dx. Whatever be the power of x, that is nothing but x raised to n1. And basic formula x raised to n into dx equals to x raised to n plus 1 divided by n plus 1. So work done equals to k as it is x raised to n means 1. So 1 plus 1 it becomes a 2 divided by n means 1. 1 plus 1 divided by 2. No dx plus constant of integration. Assume that constant of integration is a 0. So the term becomes work done equals to half of kx square. That is the work done equals to half of kx square. Or that work is stored in a form of potential energy. And that potential energy is kind of writing completely. Is half of kx square. This is my first equation. Now we calculate the particle performing some displacement, means the particle is in motion in this way. Now we calculate the kinetic energy. Now the kinetic energy, basic formula for kinetic energy is what is the basic formula for kinetic energy? It will be very simple. Kinetic energy is given by half of mv square. But what is V? V is velocity of particle and it is given by omega into a square minus h square. Then V square becomes omega square in bracket a square minus h square. Let me substitute here. Then my kinetic energy becomes A equals to half of m. And V square means omega square in bracket a square minus h square. This is my second equation. Now we calculate the total energy. Now it is very simple. Total energy is nothing but it is the sum of kinetic energy and potential energy. The kinetic energy is given by half of m omega square a square minus h square. And the potential energy formula is half of kx square. Okay? Here m omega square and there is a k. But when you study the differential equation of linear SHM, at that time omega square equals to k by m. This k equals to m into omega square. Let's substitute there. This formula includes number of formulae. Okay, and it's very important to reset all the formulae. Now I am substituting the value of k as a m omega square. So my equation becomes half m omega square a square minus x square plus half m omega square into x square. Now it will be very simple. the total energy equals to half of m omega square. If part is a common, a square minus x square plus x square. Here x square get cancelled, and we are getting total energy equals to half of m omega square a square. This is the formula for kinetic total energy of a particle performing linear acceleration. Here we see the three formulae which are very easy. Work done is stored in the form of potential energy, and it is given by half of kx square or half of m omega square into x square. Kinetic energy is given by half of m omega square s square minus x square, and total energy is given by half of m omega square a square. Let's see once again. Potential energy half m omega square x square. Kinetic energy half m omega square s square minus x square. Total energy half m omega square a square. Okay, these are the three important formulae. In other way, the same expression is given. Total potential energy is given by half of m omega square x square. Just I am making one small list of this formulae, so it is very important. Making a list of all the formulae. Like the three formulae: potential energy half m omega square x square. Not erasing this diagram. Potential energy is given by half of m omega square x square. When a particle performing linear acceleration, the value of x is what? The value of x is, that is x means the displacement, is a sin omega t plus alpha. So I am making a square here. So potential energy equals to half of m omega square x square. Okay, x square means what? Square of what? X square equals to what? Square of all the term. That is a square into sin square omega t plus alpha. So I am writing here a square sin square omega t plus alpha. Okay. Velocity is given by, velocity is nothing but derivative of displacement with respect to time. Now take a derivative of this. That is nothing but a sin of omega t plus alpha. Its derivative is the cos of omega t plus alpha into omega, because we are differentiating with respect to time. So a omega into cos of omega t plus alpha. So v square. So my formula for kinetic energy is what? This is first. Remember that this is a formula for potential energy. Kinetic energy is given by what formula? Half of m square. Okay, directly I am substituting the value of v square. This is the formula for v. I am making a square and substituting here. Therefore, just I am highlighting in this way. This is potential energy. V is given. So v square equals to a square omega square cos square omega t plus alpha. Therefore, kinetic energy equals to half m. Okay, half. This is formula for potential energy. Kinetic energy formula half m v square. M v square. V square means a square omega square cos square omega t plus alpha. This is formula for the kinetic energy. Okay. Now total energy is nothing but what? It is the sum of potential energy and kinetic energy. Therefore, my total energy becomes what? Total energy becomes half m a square omega square, taking us on this, half m omega square a square, and the variable term is sin square omega t plus alpha and cos square omega t plus alpha. Let's substitute this sin square omega t plus alpha as one. Just substitute as a theta. Cos square omega t plus alpha as a theta. So in bracket it becomes a sin square theta plus cos square theta. Plus what is the sin square theta plus cos square theta? It is nothing but a 1. Therefore my total energy becomes, it is nothing but a half m omega square a square. This is also a shortcut or a trick to remember the formulas of potential energy, kinetic energy and the Okay. Now we see how you graphically represent the variation of energy at the mean and at the extreme positions. Okay, that we have to see first. That is the graphical presentation of energy. For that, on the y-axis, just show and like so. This y-axis corresponds to energy. Means we are plotting a graph of energy versus displacement. This is my displacement. Right? This is my mean position, where the displacement is 0. This is my positive extreme position, where displacement is a plus a. This is my negative extreme position, where displacement is minus of a. Okay, and the maximum total energy is how much? Maximum total energy, its value is a half m omega square a square. Okay, now we see when the particle is at mean position. Just I will show by this orange color. When a particle is at mean position, value of displacement is 0, means the potential energy is 0 at the mean position. Okay, at extreme position, x equals to a, means the potential energy becomes half m omega square. X equals to a plus a, so square of that is also plus a. That is the value of potential energy. At negative extreme position, x equals to minus a. Square of minus a is again a square, so potential energy becomes half of m omega square a square. Therefore, the potential energy graph it will be used like this. This is my potential energy. This potential energy is minimum at mean position, maximum at the extreme position. Now, see the another term by the being shown, that is the kinetic energy. At a mean position, x equals to 0. Kinetic energy. Okay, we require the formula. Kinetic energy is given by, here just I am writing the formula, half of m omega square a square minus x. This is the formula for kinetic energy. Now, at the mean position, x equals to 0. So x square becomes 0. Bracketed term becomes only a square. So total energy becomes half of m omega square a square. This is the value of kinetic energy. At positive extreme position, x equals to plus a. So there is a x square. X is plus a. So its square is a square. So a square minus a square 0. Bracketed term becomes 0. Therefore kinetic energy becomes a 0. At negative extreme position, x equals to minus a. X equals to minus a, square of x. So square of minus a, it becomes a square. A square minus a square 0. Entire term becomes a 0. Therefore kinetic energy radiation it will be looks like this. This is my kinetic energy at mean and extreme positions. Okay, kinetic energy is maximum at the mean position, minimum at the extreme position. Potential energy maximum at the extreme positions, minimum at the mean position. Now one is remaining, that is the total energy. Now this will be very simple. Total energy. Total energy is given by half m omega square s square. X equals to 0, but it is independent of displacement. Total energy is constant at every place. Therefore, graph of total energy versus displacement, it will be this like this. This is my blue color is my total energy. Okay, this is the graphical presentation of energy at mean and extreme positions when a particle is performing simple harmonic motion, or displacement energy versus displacement graph of a particle performing oscillation at mean and extreme position is looks like this. Okay, now we stop here.